Let us start today's lecture on recapitulation of certain items which I have taught to you a few days before. First of all, our important thing is to clearly clarify the principal stress and principal strain. What we are supposed to do here, to clarify the matter, we have to recapitulate one thing again. What is the angle between two straight lines before and after the deformation in a three-dimensional axis, three-dimensional coordinate axis? What is this here? PQ, just one second. Let PQ be a line element with direction cosines nx, nx1, ny1, and z1. What is PQ? Is like this. Now, let PQ be a line element with direction cosine. This is the line PQ. This is the line PQ. This is the line PR. It has a line element with direction cosine nx1, nx2, nx1, ny1, and z1, which means it is subtending an angle whose cosine with three-dimensional axis with whose cosines are given as x1. We went with the angle about the angle subtended with x-axis, and ny1, the cosine of the angle subtended with y-axis, and nz1, cosine of the angle subtended with z-axis itself. And PRB, another line element with direction cosine nx2, ny2, and nz2. And theta is the angle between the two lines element before the deformation. After the deformation, the line segment becomes P dash Q dash, P dash, and P dash R dash. Which is P dash Q dash and P dash R with individual angle theta dash. So theta became theta dash. We can determine theta dash easily from the relation itself. For analytical geometry, you know that nx2 and nx2 dash, nx1 dash cos theta dash, which is equal to nx1 dash, which is the direction cosine of PQ, and n y dash and z dash is the direction cosine of PQ in the new position itself, and x dash and ny z and n z dash direction cosine of PR and the new position itself along after the deformation itself here. It was initially was theta and now becomes theta dash. Initially, its direction cosines were nx1, nxy, ny1, and z1. Now it becomes nx1 dash, ny1 dash, and z dash dash. And initially it was nx2 dash, ny dash, and z2 for PR. Now it becomes nx2 and nyz2 and nz2. And as for the analytical theory of analytical geometry, cos theta dash is the multiplication of respective directional cosines and adding them together itself for a three-dimensional coordinate axis. So that theta dash means the angle between PR dash and PR dash, angle between P dash R dash and P dash Q dash will become nx dash into nx dash 2, nx ny1 dash ny1 I2 dash and nz2 1 dash or nz2 dash itself. Now the values of nx dash, nx1 dash, ny1 dash, nz1 dash, and nx2 dash, ny2 dash, nz2 dash is available from the equation 27 already reduced, and neglecting the squares and production of the small strain components, cos 2 dash is equal to 1 by 1 plus pq, 1 plus pr, etc. 1 plus 2 n 1 plus 2xy, nyzz, and 1 plus 2y, ny, nz1, z2, and gamma x1, gamma x2, and gamma x3 like this. But it's such a big equation like this. If the two line segments PR and PQ are at right angles to each other, then after the strain cos theta dash, which may not be equal to 90 degree, will become 2 into f psi x Now, all these squares and that we made, we reduce this like this, cos theta dash will got the similar function of the angle equal itself. But now, if the two line segments PQ and PR are right angles to each other, if we assume like this, then in order to now, then after the steering, cos theta dash will, all this, it will be, after simplification, it will take this particular form where you see 1 nx1 nx2 and 1 multiply nx1 nx2 and ny1 ny2 and nz1 nz2. These are all equal and they become twice here. 2 into 2xy nz like this. Now 90 degrees theta represents the change in the initial right angle, and that is denoted by alpha itself. Then theta dash is equal to, next theta dash becomes equal to 90 degrees minus x itself. X goes to 18. Then cos theta dash is equal to cos 90 degrees minus alpha. So sin alpha more or less is equal to alpha itself. The alpha becomes very small. Then the shear strain becomes PQ and PR. Shear strain alpha, PQ and PR between, if we represent the relation of PQ and PR at x by alpha by x dash y pi dash axis, make gamma x dash as P cos theta equal to expression is given in equation 36, and 37b, which is already reduced here on the side here. Now, let us go to the principal axis. We are not going to that go to this once again. Just 1 second. Take that. Stop share. Okay. Oh. Let us consider a displacement field and principal axis of strain and principal strains. What is this? So let us consider a displacement field at any point P. Displacement field means a displacement vector which is defined for a particular volume of matter within 3 rectangular coordinate axes, and it is defined and proved that if the direction cosine is given for a matter and the coordinates of different points of initial points are there available, then we can get the coordinates of other points for after the deformation of the body itself. Now, the relative extension at P in the direction PQ is given as, we have already deduced here, f sub PQ, the change in length of the line PQ is given as f sub XX, which is the strain along x-axis, f sub YY y-axis, f sub z-axis, gamma XY is the shear strain in XY plane along y-axis, and gamma YZ shear strain in YZ plane along z-axis, and gamma ZX shear strain along in YZ plane along z-axis, and all are multiplied by nx square direction cosine at x-axis, and y square direction cosine at y-axis, and z square direction cosine at z-axis, and nx, ny, nz, nx, ny. So, if we know the values of nx, ny, nz, so we can have, means we know the displacement grids potential where displacement vector where is given up, say PQ is equal to ux into I, uy into y, z into j, and uz into k. So ux, uy, you are the direction cosine itself, and if we know the value of them, then we get different values of PQ. Then nx, ny, nz are known. If you have, then you have to know the fx, uy, ez, and gamma xy, gamma yz, and gamma z. Only then we can calculate the value of the eccentricity of the length PQ. Now, we should understand the following questions. What is the direction along which strain is an extremum? Our problem, our motto and target is to know the maximum strain and minimum strain, and what is this value, and what is the orientation or direction of this of this particular position or particular line PQ, which is the maximum, which has the maximum strain, and what is its orientation along x-axis, y-axis, and z-axis. So what we have to know the amount of maximum strain, and we have to know the direction cosine of the line with which has the maximum strain. So this is the, and what is this value? So in order to do so, we know always we use the calculus and we do the maximum. In order to find maximum minimum, we have to equate EPQ, differentiation of EPQ in terms of NX, differentiation of EQ in terms of Y, and differentiation of PQ in terms of Z, and we have to put them equal to 0. So in a calculus, we always do like this. We make the derivation along that particular with respect to the particular element parameter and equate it to 0 to get the maximum coordinate maximum value of the parameter with which this particular value is equal to got the maximum value. So this first we have to know whether nx, ny or nz are independent or not. Means their independent means their value does not change with the change in value of ny and nz. But in practice, nx, ny or nz are not at all independent. They are very much dependent because it is the direction cosine of a particular straight line. It is the cosine of the angle this particular element PQ subtend along x-axis and y-axis and z-axis. And if you have any change in nx or any change in the orientation with x-axis, then orientation with y and z-axis must change. Otherwise, this thing will not hold good. So we know that all intermediate sets they are related by the relation nx square plus ny square plus nz square is equal to 1. So they are not at all independent, they are dependent, they are related with each other as per this equation itself. Now, what happens here? If we say, we just consider or assume nx and ny are independent each other, but we are not talking anything about ny, hz. And they differentiated that above equation ns square, ny, z square, this equation by means of nx and ny. So we get 2nx square, 2nz, nz by dx equal to 0. Similarly, 2ny and 2nz, which dnz is equal to 0. Similarly, we can assume ny and nz are independent but not anything about nx. Then this equation again we can differentiate in terms of ny and nz and get the respective values like this. Now, next we differentiate EPQ with respect to nx and ny first. And so it will get this particular form, and we have got nz and nx here. Here, as they are independent, as nx and ny is independent of nz, so if you differentiate ny in terms of nx, that will become 0. This conception we are using. But here we are saying nz may not be independent of nx, so we can derive them, we can make the derivative over it. They are not constant they may change with the change of nx, then it may change. So we can make the derivative here. But we are sure that nx and ny are independent. Means if we derive ny in terms of the nx, that will be equal to 0, or if we derive nx in terms of ny, that will become 0. So this equation takes this particular form here, where nx is there, then where ny is there, then that is become 1, and others at ny and nz itself, it take this particular form, and nz and nz here, and nx, ny and nz, these are all the multiplication will have this particular term. Similarly, for y, if we differentiate it first of all in terms of x, then in terms of nx, and in terms of y, it will take this particular form itself, and both are we are equating to 0 itself. So what will happen? Stop share. Then we substitute dx and dnz from this equation 38. We have what we have got by multiplying nx square plus ny square over nz square equal to 1 equation by first nx with respect to nx and then with respect to ny. Then we put the value of nz and nx and nz and ny here, and we'll get this relation like this and like this. And similarly, in what we have told here earlier, we have to make ny and nz are independent of each other, but nx may dependent, and we process the same failure, we'll have the same equation like this. And you see the right hand side of this equation are equal. This is equal to this equation, but left are not equal to each other. They are different. And if we say the right hand of the equation, if we put 2 epsilon equal to this right hand portion of the equation and rearrange it again, then this equation become take this particular form here this line remains here, and 2 into epsilon into nx, and this line remains here as it is minus 2 into epsilon y is equal to 0, and the third equation, third relation is not shown. It is equal to 2 into epsilon z equal to 0 itself. Now, we have three such unknowns, nx, ny, and nz, and we have three equations, and we can get the value of nx, ny, and nz which determines the direction along which the relative extension is extremum or maximum. But let us assume this direction is determined, the last equation by nx, second by ny, and third by nz, and adding them together, the equation will take this particular, these three equations will take the particular form itself. Now, we know that nx square plus nyz square, ny square plus nx square is equal to 1. So right hand side becomes 2 epsilon, and left hand side is equal to the 2 pq, 2 epsilon pq. So epsilon pq is equal to epsilon itself. So we can replace epsilon pq in future calculation by the use of epsilon only, which it is valid. What's the difference between the two? This is the eccentricity along PQ. I mean the strain of the straight line PQ. And it is the strain of any line which is not shown here, which is determined by this type of particular equation itself, which is determined this equation. When no, its x-axis is strain along x-axis, y-axis, and z-axis, and shear strain along x-axis, x, y, and z-axis itself. If we know these strains, and we'll have this ratio epsilon will become equal to this thing epsilon, and nx1 we are supposed to know, we'll get the value of the maximum strain itself. The value of nx, ny, z after determining direction along with the relative extension is extremum and further. The SI is equal to 3 extremum. Now, the earlier equation can be written as just we put the f side x, f side x minus f side nx, and others remain same. Here, this one remains same, f side yy minus f side into ny. This one remains same, and third is f side zn minus f side nz will remain same. If we put gamma, half gamma xy is f side xy, because we know the maximum value of shear stress is exactly half of the maximum value of tensile stress itself along the same line direction on the same plane. If we replace them, this equation will take a further form like this. And it's 20. This equation will take this particular shape here. And if we plot a vector matrix here, then this, and this will be like this, and this one, and this one is like this, and this one is like this itself. And if we expand this determinant, it will take, from the theory of variant, epsilon square minus j1 epsilon square plus j2 epsilon minus j3 epsilon itself. So we have to know first the value of epsilon j1, j2, j3. What is happened? J1, we know from the equation of variance, epsilon xx plus epsilon y plus epsilon z. J2 is a direction matrix like this, and like this, and J3 is a directional matrix like all these things. We should know that J2, important to observe that J2 and J3 involve epsilon yz, epsilon y, xy, epsilon yz, and z, but not gamma x1, gamma x1, gamma 2. It is a similarity principle, and so here it's all in terms of the longitudinal strain. Not there is no gamma. The value of gamma strains are not shown here. This analysis is similar to principal stress axis and principal strain. For a given stress of strain at a point P, the relative extremum extension f psi is an extremum in a direction n. Then f psi is the principal strain at P, and n is the principal strain direction associated with P. So much things we have learned to say f psi is an extremum, and n is the direction of this extremum itself. So this big equation becomes 21. This division strength becomes epsilon 1, epsilon 2, epsilon 3 in the root of each epsilon cube minus j epsilon 1 and epsilon 1 j into epsilon square plus j2 into epsilon plus j3, where j3 is the third variant of stream and j3 we have neglected because it will become too small to show because it is a multiplication of all the extension and we can neglect it as too small to ignore. The principal direction these are obtained by epsilon I. So we, in place of epsilon, we are putting the value of I itself, means 1, 2, 3 direction. Difference is that we want to have the value of three principal strains, which is epsilon 1, epsilon 2, and epsilon 3 from here. So we are putting the value I here to denote them. Once it will be epsilon x1 is epsilon 1 and so here 1 f6 is epsilon 2 and with so and so here and epsilon x6 is epsilon 3. So 3 epsilon 1, 2, 3 are distinct and means requisitely different from something else of a similar type. It is distinct, means it is clear and profound. Then the axis of each of them, n1, n2, and n3 are also unique and they are mutually perpendicular. If say epsilon 1 equal to epsilon 2 but not equal to epsilon 3, and then this axis n3 is unique, and every location perpendicular to n3 is at a principal strain associated with epsilon is equal to epsilon 2. If epsilon 1 is equal to epsilon 3, then every direction is the principal direction itself. Then all three directions are equal to principal directions. Let us quickly go through this technical analytical problem itself. We have the problem, numerical problem here. Displacement field in micro units for a body is given as u x square plus y into I, 3 plus z into j plus x square plus 2y into j. So nx, ny, and nz is given. Principal strain defined by the principal strain at point P. Say P is the coordinate. Those coordinates are given 3, 1, and minus 2, and the direction of minimum principal strain. So first, what is given to us? The direction displacement field or displacement cosine, which is given by x, y, and z itself, and the principal strain we want to know for a particular point whose coordinates are also given to us. First of all, we have to displacement coordinates are first we have written down here. Then we have to find out epsilon xx, epsilon yy, epsilon zz, and which is the derivative of dux by dx, dy by dy, etc. Epsilon yz, xy is the addition of these two derivatives. Epsilon yz is addition of two derivatives, and epsilon z is addition of two derivatives. All we have deduced earlier. So x square, epsilon x is equal to 2x here. Epsilon y, there is no y term, is equal to 0. Epsilon z, no z term, is equal to 0. And this plus this is epsilon y is equal to 1. This plus this epsilon y is equal to is equal to 3, and dx plus, if we put the value, it will become 2x itself. This is equal to 2x. Next, x point 213, dux is equal to 2x and duz is equal to 3. And duy is here, duy, okay, and duz equal to, if we put the both are equal to 0, and yes, these two are equal to 0, and thus the if we put the value of z, it will become equal to 3. So exs equal to 6, y equal to 0, and ez is equal to 0, gamma xy is equal to 1, gamma yz is equal to 3, gamma z is equal to 6 itself. If we put the value of x, y, and z from these two equations, this will take this particular form. So the main state variance here, J1 xx plus y plus z, which we add together is equal to 6, J2, we put all the value equal to 23 by 2, and J2 and J3 are unique, then involve xy, half gamma xy, gamma y z, and put the value of respectively J3, ex, exz, ey, and ez accordingly. So the J3 is to take this particular form of matrix itself is equal to -9. The cubic equation will take this particular form itself, f star minus 6 f star plus 23 by 2 f star 3 f star plus 9. From the standard method, which we have already gone through, first we put the value of p and q and r here, where a numerical value of p, q, and r is given here, are constant given here, and we then substitute y is equal to x half 1/3 into p, and it will give x cube into ax plus b is equal to 2 itself. So y here replaced by 1/3p, where a is equal to 1/3 minus p square, b is equal to 1/27 3p square minus 2pq into 2r 27r itself. And cos p is given by this particular relation p, a, and c. Now y1, y2, and y3, these are all given here. So you can calculate by knowing the value of a, b, and c is known from pq1, value of pq and r, which is given here. So a and b, p and q is also given here. So a and b know, then cos phi will know. Then from cos phi and p, cos phi and p here will get a into b, and cos phi is equal to 964 itself. And thus the principal stress epsilon 1, if we put this value in this equation, respective equation, we get epsilon 1 is equal to this, this, and this. And the first intermediate becomes 6. First, the amount, second invariant becomes like this, third invariant like this, which is -9. Thus the equation, the maximum principal strain is equal to -2. Minimum principal strain is -2, and then with this, from these three equations, the solutions are nx, this, and this, and this. So numerically, it can be solved unless you know numerical values are given. This equation becomes too complex to understand. Becomes it's 23. Now They should be 55 is not here. 56. So you have to go here. 55. That's not coming. Too big. জায়গা দিতে পারছে না। Now, the plane state of strain. Now, in a given state of strain, there exists a coordinate system OXYZ such that epsa ZZ, epsa Y, gamma YZ, and gamma ZX. Epsa ZZ is the extension strain or longitudinal strain along Z axis, shear strain along on YZ, along Z axis, shear strain on ZX plane along Z axis, X axis itself. So three are all equal. So Z axis don't have any type of stress itself. So the strain becomes totally two-dimensional in case of three-dimensional itself. Now the state of stress is said to have a plane state of strain and parallel to the XY plane. This is a situation which is called plane state of strain. Means not rectangular but plane. Means acting on a state of strain is acting on a plane not in three-dimensional direction but on a two-dimensional direction only. That is on XY plane. The non-vanishing strain components are such epsa XX, epsa YY, and gamma XY. So two elongated tensile strain and one shear strain itself, which is in the axis X and Y. And PQ is the line statement of this X plane. Then the direction cosines with the direction X and NY, then all the relative extension of the line PQ, all it will reduce to epsa XL, NX square, epsa Y, NX square, and XY, NX, NY. All other terms are reduced to 0, are eliminated. And if you make an angle theta with the x-axis, we put NX cos square theta and NY cos 90 minus theta is equal to sin theta, and NXY, NY gamma half gamma XY sin theta cos theta. We know the two-dimensional strain of stress, epsa 1 and epsa 2 are the principal strain itself, and epsa 1 epsa 2 is equal to epsa x epsa y by 2 plus square root of epsa x minus epsa y 2 whole square plus gamma xy gamma epsa 2 whole square and total square root of itself. Now we see epsa 3 NZ is also a principal strain, but the strain makes the angle theta and theta plus 90 degree with the x-axis such that tan phi is given by this equation. And this conclusion will be identical that with the stress, if we access xy, xz and xz in place of sigma x, sigma y, sigma z respectively, and xy half and half, then epsa x and epsa y put like this and respectively itself. The principal strain axis of strain remains orthogonal after the strain itself. How? PQ is the principal extension of strain cases with direction nx, ny, and nj. And as per equation, epsa xx minus epsa yx, same equation we have replaced. Here we are replacing with epsa 1 and epsa 1, and others are here same. Here nx1, nx2, nx1, ny1, nj2, this is for PR. And this is the equation cosine for pq.